Okay, this is part 2 of 2 on our lectures covering chapter 9 in your book on experimental design and hypothesis testing. In the previous part, we had talked about one of the two basic designs that we see in experiments, and that was the between subjects, or aka independent groups design. Now we're going to move on and talk about the second major design type, and that's within subjects. So, as I said, the terminology can be a little confusing. The book actually uses both of these. I'm going to try and stick with the distinction between subjects or within subjects. So this is a within subjects design that is also referred to as a repeated measures design, which is a description. It's not it's differentiating it from a between subjects design. It's telling you what the process itself is. So that's the reason why we have the multiple terms. But I will try to stick consistently as much as I can with a within subjects design. We alluded to this, the second article we discussed at the beginning of this chapter was the example we wanted to use of a within subjects design. But what distinguishes this from between subjects is that all participants receive all levels of the independent variable. You're comparing the performance of the same individual across all the different conditions of your independent variable. Whatever levels of your independent variable are introduced through your manipulation, that individual will receive every level of that independent variable at one point or another, right? And we'll talk about ordering in a moment. But essentially, what you're doing is you're introducing the individual as serving as their own control. So you're controlling for whatever individual differences they bring to the table. Well, it's the same person at each measurement of the dependent variable. Therefore, they serve as their own control is the phrase that's typically used. Whatever their individual differences are, they're still that person at each subsequent test as they go through the various levels of the independent variable. The other reason why you might prefer to use a within subjects design is that it requires fewer participants, right? You get a point of data, at least one point of data from every single time that person experiences a level of the independent variable, you get a point of data. So a single individual in a simple, just a two-level independent variable where like experimental and control doesn't make sense in this, but basically just say you have two treatments that you're comparing your new treatment and then like the standard treatment. You want to see if you've improved upon it. Well, that individual gets administered the standard treatment and the experimental one that you've designed. And so as a result, you receive 2 points of data from that same individual. So as you can imagine, the more levels of the independent variable, that's how many points of data you get from each individual. So you require fewer individuals, a smaller sample size in a repeated measures or within subjects design than you do in a between subjects design where each person only experiences one level of the independent variable exclusively and therefore really gives you like 1 point of data. It's also desirable to utilize a within subjects design when the experimenter is sure that the effect of one treatment does not carry over or contaminate the other level of the treatment. Just based upon whatever it is you're doing, it might make sense logically, or you might be able to show this statistically that there's not a carryover effect, there's not a practice effect, that whatever you do in one level doesn't then influence necessarily how the person experiences the other level of the independent variable. So if you have that type of design, if you're testing those sorts of characteristics, then it's fine to utilize within subjects design because you're maximizing, as I said, the amount of data you're getting from each individual, and they're serving as their own control and hopefully accounting for individual differences and pulling that out of the analysis in certain ways. As you can imagine, this type of design is essential for a longitudinal study. If you want to look at how the person is changing over time, then a repeated measures design is really helpful. So this is an example, just a graphic from your book that explains a within subjects design of repeated measures. So as you said, and as we saw in the previous image, in the previous part of this lecture, each of these represents an individual subject, right, a participant in the study. Each individual subject then receives the pretest, right? You have to get a baseline measurement of whatever your dependent variable is going to be, whatever your outcome is. They then go through the control condition, presumably. Then they go through the test condition. They go through the test is a test, not a post-test. You measure. They go through the control condition, and then you measure the difference. They then go through condition A, for example, and then you test them again to measure the difference. And then finally, they go through the third condition, condition B, and you have a final test, which in this case we're referring to as the post-test because it is the last one administered. These tests along here, the pre-test, the test A, test B, and the post-test here, may all be the exact same measurement tool. You might be giving them the same questionnaire or checking the same vital sign or whatever in your study. But as you can see, each individual subject receives all levels of the independent variable. As I mentioned, you have to be wary or at least mindful of carryover effects. So, a within subjects or repeated measures design may not be the right one for you in terms of what you're studying if there is a strong carryover effect from whatever it is you're doing. So results can be confounded by carryover effects in a variety of forms, right? The first is the order of the presentation of the conditions. If you look at that previous slide, everybody went through the control, the A, and the B in that sequence. There might be something about the order of administration that produces a carryover effect, right? So there might be a reason why if you receive treatment B at that point in time, it's going to impact, for example, how you receive treatment A. It might be something very routine. It might just be that by the fourth time the person sees the test, it's been a few hours and now they're fatigued, they are losing focus, so that could affect it. So the order can have a factor in affecting their performance on the dependent measure just by virtue of the time that's passed or fatigue factors. It might be they become more familiar with the measurement or there's a practice effect. And so as a result, they're just scoring better no matter what because they've seen the test multiple times. Or it might be that whatever your manipulation is that you're doing has this build-up effect where whatever happened in treatment A carries over into treatment B and is still influencing their performance. There are a few ways to control for this. If you think there's an order effect, you can just randomize the order. So you can randomize the order in which the levels are presented if that's possible. It's not always possible based upon what you're studying. But if possible, what you can do then is this person comes in, they receive treatment B, then treatment A, then control. The next person comes in, they receive treatment A, treatment B, then control. The third person comes in, they receive control, treatment B, treatment A. Every possible combination thereof can be randomly presented. The problem then is that you find that if you truly randomize, you may just statistically by chance end up with more participants receiving a certain order than others. So another solution besides randomizing is what's called counterbalancing. And this is where you basically ensure that each treatment or level of the independent variable occurs in each time period of the experiment. So every possible combination is represented. There's one called complete counterbalancing, in which case you have to basically figure out what are all possible orders of presentation and make sure that I have some in at least one individual in every single one of those, or I have 10 or 100 or 1,000 in each group that received that order of the variables. That can be very tedious, that can be very difficult, and can start to get unwieldy very quickly. So as the number of conditions of your independent variable increase, the number of possible orders increases. For example, let's say you had 5 treatments or 5 levels to your independent variable. Well, now you have 120 different possible orders of presentation. So that's essentially, for math, we call that a factorial, right? It's sometimes represented as a number with an exclamation point after it. So 5 factorial is 5 times 4 times 3 times 2 times 1. What you get is 120 different possible orders. 4 treatments would have 24 different orders. 3 treatments itself even has 6 different orders. A way you can combat this is something called a Latin square design. It's a way to combat confounds and carryover effects in a within subjects experiment, but it's an incomplete counterbalancing. But each possible order of treatments occurs equally. So what happens is you order your treatment levels in they receive it, and participants receive it in a varied order, and you basically have to calculate a sample size that is the multiple number of treatments in the Latin square. So I'm not going to test you too much on the details of the Latin square, but your book goes into it in some detail as well. But it's just a way that's a little more manageable than complete counterbalancing. So here's an example of a repeated measures within subjects design with counterbalancing the order of the treatments, right? So as we said, with three treatment levels, 3 levels of your independent variable, what you get is 6 possible combinations. So in this case, we would have a group that went ABC, we'd have a group that did ACB, we'd have a group that did BAC, group that did BCA, so on and so forth, every possible combination represented. This is meant by doing this, by introducing every possible combination, it allows you to look and analyze for carryover effects. You might find there is none, and this was done just as an insurance, but you might see that I can actually statistically see which treatments have a carryover effect, how the order impacts their performance on the post-test, which is done at the end. Okay, now I'd like to talk about null hypothesis significance testing, which is sometimes abbreviated as NHST. I know that's a bit of a mouthful, but this is a really important subject for research methods. This is at the heart of how modern studies are conducted and how we talk about causality in an experiment. So we utilize statistics to test the relationship between the independent and the dependent variable. What we want to know, let's say that I observe a difference between my experimental group and my control group. As we've discussed in the class, that difference might be due entirely to chance alone. Okay, it might just so happen that through random assignment, I put people in the treatment group who were doing better on the outcome to begin with. There's all various reasons why, just by sheer chance alone, you end up with groups looking different than one another. What null hypothesis significance testing is doing is it's trying to determine how confident are we that that is not the case. Okay, so I want you to, there's a lot of negatives in this that you have to wrap your head around. But the idea is that the probability as to whether or not the results of an experiment are due to chance alone is referred to as statistical significance. So we set statistical probabilities at a level of significance that we feel comfortable with, and this is usually indicated by what's called a p-value, right? Traditionally, p-values are set at what's called 0.05 or less, indicating that an obtained finding is statistically significant. Let me walk through what that means. That statistical significance simply means that that particular outcome that we have in our study is unlikely due to chance at the 0.05 level or less, meaning 5% or less. So what we're saying when we say something with a p-value of 0.05, which again is the researcher decides what the p-value is. 0.05 has been used as a standard for a long time, but you'll see plenty of studies where they use 0.01 or even smaller numbers. You don't usually see anything bigger than 0.05. But what you're essentially saying is if my statistical test spits out a p-value less than 0.05, it means there's a 5% chance or less that the relationship that I'm seeing between this independent and this dependent variable in my study here, this particular study, is due to chance alone. So it gives us a small amount of confidence that what we're getting at, what we're measuring is valid, right? That we're actually seeing a real thing, a real relationship between these two variables, this independent and dependent variable. Statistical significance testing utilizes something called the null hypothesis. From math, null generally means not, zero, absence, okay? So it's a negative term. But the null hypothesis is basically the hypothesis that there is no difference or relationship between the two independent and the dependent variables. The null hypothesis is essentially that we were wrong. Okay, that there isn't a relationship between the independent variable and the dependent variable, a causal relationship. It doesn't do anything. It's just not there. That hypothesis we refer to as the null hypothesis, the lack of a relationship between the two variables. In contrast to that, we have our research hypothesis, the thing we're proposing, right? The prediction of a specific relationship between the independent and the dependent variable. A significant result tells the researcher, a statistically significant result, tells the researcher that they can reasonably reject the null. Now, this terminology can be very confusing, so I'm going to go over it a couple times. What it essentially tells them, if you have a statistically significant finding, is I can reject the null hypothesis. I can reject the hypothesis that there is no relationship between the independent and the dependent variable. But very importantly, and this I want you to really sit with this for a moment, is it does not mean that you can then accept your hypothesis absolutely. Okay? You really are only talking about the ability to reject the null. There is always a level of tolerance for uncertainty in this type of research, because that is the nature of the world in which we live, right? There's always the possibility that there's error, that there's bias, that there's just random chance that I just happened to, by flipping a coin, it came up heads 10 times in a row. Is one way to think about it, right? Random assignment is not perfect. It has the potential for patterns to emerge by chance, randomly, but those patterns can then have an impact. So when we find a statistically significant finding, this is really important. What you're then saying is, I can reasonably reject the null hypothesis. I can reject the idea that there's no relationship between these things at all. What it does not say is that I can say with any certainty for sure that my alternative hypothesis, my research hypothesis, is correct. And that can be a little hard. Let me give you an example from the monkey study, the study on brain plasticity training. Remember, trying to improve people's cognitive functioning. The null hypothesis in that case would have been brain plasticity training doesn't do anything. It doesn't change. You're not going to see any difference between the two groups, whether or not they received it or not. The alternative hypothesis, the research hypothesis that they held, was brain plasticity training results in higher scores than in groups that receive either a control or a sort of an educational DVD that has nothing to do with brain plasticity. So this is at the heart of null hypothesis significance testing, is understanding this idea of what the null hypothesis is, that there is no relationship, and that a statistical test tells us whether or not we can reasonably reject the null hypothesis. In that decision, in that process, where we decide whether or not we have enough evidence statistically to reject the null or not, we have these two types of errors that can happen. And these are essentially mirror images or the opposite of one another. And we refer to them in science as type 1 and type 2 errors. So these are the two types of errors that we have to weigh when we're making decisions about whether to reject or accept the null hypothesis. Accepting the null hypothesis essentially means accepting the hypothesis that there's no relationship between the two variables, right? When we make that decision based upon our evidence, based upon our statistics, and based upon what we see in our study, we know there's a chance that one of two things, one of two mistakes could happen. A type 1 error is when the null hypothesis is wrongly rejected. Okay. Essentially, what you're saying is that I'm rejecting the null hypothesis. I'm rejecting the idea that there is no relationship between these variables. But in fact, in reality, there isn't one. And as you know, with the p-value of 0.05, you're still saying there's a 5% chance that this observed relationship, even though it doesn't seem unlikely, it could still just be due to random chance alone. So that's a type 1 error, is essentially when you reject the null when in fact the null hypothesis is true. That p-value is related to another statistic that we call the alpha level. They're the same thing. When I say I'm setting my p-value that I'm looking for at 0.05, what I'm really saying is I'm setting my alpha level, my willingness to make a type 1 error, at 5%. So that's what I said. There's always, even with a p-value less than 0.05, it means there is a less than 5% chance, somewhere in there, up to 5%, that the null hypothesis is true, even though I've had pretty strong findings. So I'm setting a level at how willing I am to essentially have what we might refer to in medicine as a false positive. You might think of a type 1 error as a false positive. The opposite of that, the flip side of that, is called a type 2 error. And a type 2 error is when the null hypothesis is wrongly accepted. When you accept the null hypothesis, remember what you're saying is there's no relationship between these variables. But in a sense, what happened is you missed it. You obtained, in medicine, we call this a false negative, right? So the type 1 error is a false positive. You're essentially rejecting the null, which we infer to mean there's good evidence that the hypothesis that I made may hold up. We're not saying that that's exactly what we're finding. We're just saying we can reject the null. But the counter thought to that is that means there's a pretty decent chance that my research hypothesis is right. Hence, a false positive. A type 2 error is when I was right, but I failed to detect it. I missed it. My research hypothesis is probably accurate. I wrongfully accepted the null hypothesis that there was no relationship between the variables. So type 2 error can often occur because of a lack of statistical power, a lack of sensitivity, or an ability to detect the difference between the treatments. So we know that, like, maybe the difference really is there. It's real, it exists. This difference between different levels of the independent variable and how they affect the dependent variable. But our sample size is too small, and we can't pick it up. We're not We don't have enough variation between those groups to detect the difference in a significant way. So sample size is an important factor. The other is something we've discussed previously a little bit, which is the idea of effect size. How robust is the relationship that causal relationship between the independent and dependent variable? If it's subtle, if it produces a very small change, but a real one, it's a small effect size, and therefore we may have a hard time detecting it. So small effects if it's a small effect size, it requires a larger sample size. If it's a large effect size, you may not need as big a sample to detect it. So the numbers to help determine the sample and the effect sizes are usually obtained from pilot studies or from looking at existing research in the field already that's out there in the body of knowledge regarding these variables. So this is just a little graphic that I hope helps to explain this distinction between type 1 and type 2 errors. Okay. On this axis, what we have is the statistics, right? The results of our null hypothesis testing that we do, our statistically significant tests. What we have over here is the decision that we make, okay, on this axis. If the null hypothesis is false, right, I'm going to think about that for a moment. If our statistical test comes back with a p-value less than 0.05, it's indicating that the null hypothesis, that the chance alone is not likely to have been the reason why we observe these results between these two groups, or more than two groups. And we reject the null hypothesis based upon that, then we're correct. Okay. If our statistical test comes back with a p-value greater than 0.05, and we say, okay, we think maybe the null hypothesis is true, maybe there is no connection between these two things, and we therefore fail to reject the null. You may also think of this as accepting the null hypothesis. We're also correct. Type 1 and type 2 errors occur in these boxes here. If our statistics tells us that the null hypothesis is true, that there's no relationship between the variables, and we still reject the null hypothesis, that's a false positive or type 1 error. If our statistics test tells us that the null hypothesis is false, but we fail to reject it, or if we fail to detect it, then we commit a type 2 error. So we have to balance both of these. As you can imagine, as you increase the chance, as you lower that p-value, right? As you well, I'm going to be really sure. I'm going to set it at 0.0001, right? That means that if I get a number that low with my statistical test, there must be a really significant difference between these things, and I can feel more comfortable. There's only a 0.001 or 0.01% chance that this relationship is due to chance. Therefore, I'm decreasing the likelihood that I'll make a type 1 error, right? But I'm also increasing the likelihood that I'm going to miss it, that there is a distinction between them, but I've set the value, set the bar so high that it's going to be really difficult to detect it, maybe because my sample's too small or the effect size is not robust enough. So you're always walking a tightrope by how you're setting your alpha level, your p-value that you're looking for, or you're willing to look for in your testing, that as you increase the chances of a type 1 error, you decrease the chances of a type 2 error, and vice versa. There's a fair amount of criticism and controversy surrounding null hypothesis significance testing. It has been the sort of standard operating procedure in lots and lots and lots of different types of research, not just in psychology, for a long time. So this is a very common way of analyzing data, these types of statistical significance tests that we use. You'll see them in virtually every article that you read in any journal in psychology. We have to maintain vigilance towards reducing the risk of bias in the procedures, including the statistical significance testing that we're using. So there's some people that argue that we are relying too much on this particular type of testing and that it has some problems that we need to consider. More importantly, the idea that we have accepted it as the gold standard and that we really don't question it enough, that we're losing our sense of skepticism, right, and that we're increasing our tolerance for uncertainty by utilizing this technique. So these fundamental things like this null hypothesis significance testing, the p-values that are associated, they're fundamental to modern research today, but there is some scrutiny that's been made on them. So there's a misconception that the size of the p-value indicates the strength of the relationship or the effect of the treatment. The p-value is only a statistical phenomenon. It does not really talk about the strength of the relationship. You don't say, well, I had a p-value of 0.001, therefore there must be a really strong relationship between those variables. That is a common misconception of how people interpret data. It's erroneous to think of an outcome of p less than 0.01 as having a stronger effect than an outcome of p less than 0.05. P-value indicates the probability that the outcome could have happened or the results could have been obtained given the null hypothesis being accurate. So this misconception is related to the null hypothesis significance testing because people misinterpret what p-values mean. They think that these statistically significant findings, these statistically significant results, indicate theoretical or practical significance, which they don't. We've talked a little bit about this in the class, that sometimes you can find a really good statistical outcome, but when you go and you examine the practical difference between your groups, it doesn't mean a whole hell of a lot in the real world. This is what happened with the cognitive training, the brain plasticity training study. They found a difference. They found that people who underwent this training had a statistically significant improvement in their working memory compared to those that didn't. It was a p-value less than 0.05 or 0.01. But when they looked at what that difference really meant, this was a large sample, right? What it meant was like a very incremental amount of improvement. It was consistent and it happened reliably, right? But in the real world, it didn't really mean that much difference in how that person experienced how their memory worked. So therefore, small effect size, small practical significance, but statistically significant finding. So we always have to be very wary of how we interpret what our statistical findings mean. They don't necessarily imply that our theory or our hypothesis is accurate and strong or robust in terms of that connection between the independent and dependent variable. There's also a problem that I want to mention that's going on in psychology right now, which is the idea of reproducibility and replication of a study. So reproducibility is a core principle of the scientific method. We've talked about this quite a bit, this idea of replication, right? Someone does a study, they find a result, it's statistically significant. We know that now. That means, well, there's still, a 5 or a 1 or a 2 or 3% chance that it was due entirely due to chance alone. Someone else has to go and then conduct, or that same researcher has to do that study again in a very similar way, in some cases for simple replication. We're building scientific knowledge, we're establishing more and more evidence based upon replication of findings. They need to be independently and directly replicated for us to have confidence, even though one study might show a significant finding. Effect size is often not reported in some of these studies. Only statistical significance is. And effect size, as we've kind of come to learn, is where the rubber hits the road in terms of real practical differences in the real world, things that actually mean something to us, that we can feel, that we can see, that have a real implication for a true difference that's meaningful, not just statistically significant. So that's one thing we could do to try and help with this issue, is to start reporting effect size as well as statistical significance findings. Currently, psychology is undergoing something called a replication crisis. What's happening is that we're seeing less and less ability for consistent replication. And this is potentially due to what's called a frequent type 1 error, right? People are rejecting the null. They're saying that this relationship is not due entirely to chance, when in fact they should be. And this is just a form of bias that is introduced in the way we've designed our studies, the way we utilize statistics in psychology, and the fact that we've become pretty savvy about needing larger sample sizes and doing larger scale studies, is that we are starting to run into the problem of someone does the exact same study or very similar study, and they're not getting the same results, meaning that it's likely that maybe the person who made that first study committed a type 1 error, right? So reporting effect sizes and what are called confidence intervals is now reviewed as maybe even more informative about the reliability of a research finding, rather than simply reporting on your null hypothesis significance testing or your statistical significance that you found. The way we're trying to address this then is to start expecting our peers to include things like effect sizes and confidence intervals, which are complementary to just knowing whether or not an outcome is statistically significant. So to wrap up a little bit, for a robust and a meaningful experimental design, you have to consider how you're going to design your groups. Is it going to be a within groups or between groups design, between subjects or within subjects design? You have to consider do you have a sufficient sample size? If I only going to be able to gather a small group of people, maybe I should consider a within groups design if possible. If I have access to a large sample, maybe I want to utilize a between groups design. We then have to think about how we can control for confounds, demand characteristics, carryover effects. These are all things we got to consider in our design. And your theory or the logistical, practical implications of how your study is designed might answer those questions for you. For example, if you know there's a carryover effect from your test of the dependent variable, then maybe I don't want to use a within subjects design, because the person who receives that test multiple times, it's going to change them. It's going to affect their performance. I might want to consider a between subjects design where they only see the test once. Or I might want to consider alternate forms or alternative forms, equivalent alternative forms of that measure if I'm going to do a within subjects design. So this leads us down the path of, once we have results, how do we know whether or not they're we can attribute them to chance or to our hypothesized relationship. And this gets into the idea of null hypothesis significance testing, and of course the potential for type 1 and type 2 errors. So for all this has led to the replication crisis, some skepticism about, are we relying too much on this one particular statistical approach to measuring differences between groups? But despite all this controversy and skepticism, experimental psychological research is making great strides in how we understand and intervene in human behavior, optimize function. These things do work. They just have considerations and problems we have to consider in terms of how we interpret the results and how we design our studies. All right.